Okay, so I've taken the roll already. When we wrapped up our last class meeting, we had finished up talking about cantilever beams. So now we're going to talk about guided beam springs. So let's see. So guided found in surface micromachine MEMS devices. So I'm going to try to draw a very simplistic structure here. This would be something like a incredibly simple capacitive accelerometer for measuring acceleration in one direction, which in this case would be into the board. So these guys right here are anchors. Okay. Then we have a large plate. And so this would be our proof mass. And then we're going to have a simple set of springs on the other side as well. All right, so this is the width of our spring, and this would be the length of our spring. And we can hopefully all see that we would have 4 of these springs connected in parallel. And by parallel, I mean they're all connected between the proof mass and then an anchor point that is mounted to the substrate, right? So this would be a top view. And if we looked at it from the side, oh, and let's say, just for the sake of argument, let me move this out of the way just slightly, that we were applying a point force here in the middle of the plate, and it was directed into the board. Okay. So our applied force is pressing into the top structure. So if we looked at this thing from the side, it might look something like this. So this guy right here represents our anchor, and then we have a tungsten or some type of metallic plug here that's providing contact to the surface of our substrate. This dimension right here, H, is the height of our beam. And then, so this isn't too wildly exaggerated. Let's do something like this. Let me put my other anchor over here so I can draw this as not shiddly as possible. And then we would have some sort of beam deflection like so, based on the direction of our force pushing down on our proof mass. So this is a shitty representation, but hopefully you guys can see what it is that I'm trying to illustrate. We have a mass or a plate in the center that is being deflected downward due to an applied force. Okay. So the most simplified approach to analyzing a structure like this is to consider each one of these guided beam springs, and each one of these things, let me just put a note here, is a guided beam spring because it is specifically anchored or fixed on both sides of the spring, okay? So we're going to analyze these as if they were cantilever beams with a length of L over 2 in series. Okay, that's the most simplistic way to look at these. So in order to do that, we need to kind of understand what the guidelines for combining springs might look like. So as a kind of loose tangent, let's talk very quickly about Hooke's law for parallel and serial springs. That's not how you spell parallel. My apologies. So Hooke's law, as we have seen in our previous examples, is simply force is equal to our spring constant K multiplied by our displacement X, right? So let me just make a note here. This is spring constant, and this is displacement. So if we had a situation to where we had a couple of springs attached in parallel, so something like this, where I have two springs connected in parallel so that they're each touching anchor points, the same anchor points on both sides of the spring. We'll say the spring on the left has a spring constant of K1, and the spring on the right has a spring constant of K2. If we were to apply a force to try to stretch this spring configuration out, we would see that both springs are going to be stretched by the same amount X, right? So because they're in parallel, and if we don't allow our anchors to rotate or anything like that, the springs are going to extend by the same length, okay? So from this, our total force is going to be the force applied on spring 1 plus the force applied on spring 2, which would be K1 times X plus K2 times X. We're using the same value of X because they're both undergoing the exact same amount of displacement. X and have K1 plus K2 times X, or K equivalent times X, where, hopefully very obviously, our equivalent spring constant is K1 plus K2. So springs in parallel combine like resistors in series effectively, or they combine like capacitors for those of you electrical folks and all of that kind of good stuff, right? If we were to have two springs connected in series, so let's say that we have a second situation to where we've got an anchor point that once again can't rotate or anything like that, a spring K1 in series with a spring K2, and we apply our force like so. Now we've got a situation where the same force is acting on both springs, and so the displacements are going to sum together. So we would see that our total displacement is the displacement of spring 1 plus the displacement seen by spring 2, which looks like F over K1 plus F over K2, or F multiplied by 1 over K1 plus 1 over K2, or F over the equivalent spring constant. And so rearranging things ever so slightly, our equivalent spring constant would be 1 over K1 plus 1 over K2, and then we take the reciprocal of that whole thing. So springs in series combine like resistors in parallel, or they still combine exactly like you would expect capacitors to do. Okay, so using this relationship, then, for a guided beam spring, where we're going to treat that as two cantilever springs in series, the spring constant for a guided beam spring, so I'm going to call that KGB, is going to be the reciprocal of 2. And the reason why I'm putting a 2 in the numerator here is because we're treating it as two lengths of springs connected in series. They're going to have equal spring constants, so I'm just adding those two together. And then we're going to have 3EI over half of the length cubed, where this relationship just comes from our derivation of the spring constant of a single cantilever beam spring from our last class meeting. We've added two of them together, and we're replacing the length by half of the length because we're considering the guided beam spring to be two sections of L over 2 in series. And so we can do a little bit of manipulation here. So the L over 2 quantity cubed is going to wind up putting a factor of 8 times 3 is 24 in our denominator, EI. And then the L cubed in the denominator of the denominator is going to look like an L cubed in the numerator. We're taking the reciprocal of this whole thing still. And so canceling things out, we wind up getting 12 times Young's modulus times the second moment of inertia over L cubed. And then simply using Hooke's law, the plate displacement in what I'm going to call the z direction in this case. So let me define a coordinate system here for what it's worth. So let's say that this is the y direction, this is the x direction, and coming out of the board is the z direction. The magnitude of our displacement is going to be F times L cubed over 12 EI. That's for, to be clear, a single guided beam spring. So for this particular configuration, because we've got 4 of them in parallel, what would we then do to find the total equivalent spring constant for the system? Yeah, multiply by 4, because there are 4 equal ones together. Yes. Okay, well, you're, 3, 4 class meetings late, so sit down and start taking notes, dude. All right, so the last type of spring that we're going to talk about today is a torsional spring. Sorry, am I good to move on to the next page? Okay. So torsional springs are used to create angular displacements in MEMS devices, like hopefully you guys saw when I was talking about the TI digital micro mirror arrays and all of that kind of stuff where we've got rotation, okay? So I'm going to attempt to draw a beam that is undergoing some sort of rotation, and bear with my shitty inability to draw things. So let's say that this dimension is A. This dimension is our length. This dimension right here is B. And I'm going to try to articulate this as best I can. This angle right here will be theta, and then we're applying some torque moment mt to our system. So the angular displacement observed at the end of this bar undergoing some twisting moment is going to be given by theta is equal to m sub t times the length divided by j times g. And I'm going to make some notes here. So mt is the torsional moment, and it has units of newtons times meters instead of the newtons per meter that we're used to for some of the other things that we've seen. J is the moment of inertia for the torsional bar. Typically having units of meters to the fourth power, and then G is our modulus of elasticity that we've talked about previously. Okay. So for a rectangular beam, with A greater than or equal to B, the moment of inertia is given by the following relationship, where J is equal to A times B cubed multiplied by 1/3 minus 0.21 times B over A, all of that multiplied by 1 minus B to the fourth power over 12 times A to the fourth power. So if you took statics here at Louisiana Tech, I think they typically use tables and all of that kind of good stuff. I like equations, so I used my statics textbook to look up an equation. So applying Hooke's law for torsion, our torsional moment mt is going to be our spring constant, which in this case I'm going to call K sub theta for our torsional spring constant, times theta, which is our angular displacement. Okay. So from this, our angular displacement is simply our torsional moment divided by K theta. And we already have that relationship up here for angular displacement as well. M sub T L over J times G. So we can rearrange that, and we'll wind up finding that our torsional spring constant is JG over L, or G times AB cubed, excuse me, that should be over L. One-third minus 0.21 B over A times 1 minus B to the fourth power over 12 A to the fourth power. And this is measured as in Newton meters. for a torsional moment, MT, caused by a force F applied a distance capital L away from the beam, we get an angular displacement theta of F times L over K sub theta. All right. So mechanical review over. Electrical review begins now. Are we good for me to move on to another? Yeah. So for those of you who suffered through having me for electronics, I'm going to pre-apologize. You're about to hear effectively the exact same lecture that you had on the first day or two of Electrical Engineering 335, but in a truncated form so we don't waste too much time. Am I good to go to the? Okay. Sorry for rushing through this shit. Okay, I'm gonna move on. All right, so a very brief review of semiconductor principles. All right, so let's start by looking at some energy band diagrams really quickly here. Any of you non-electrical engineering folks have any clue what the hell an energy band diagram is, literally at all?
Are you referring to the band gaps?
Yeah, so at least one of you. Great, okay. So if we were to look at different types of materials, generally the band gap, or excuse me, the energy band structure of different types of materials, typically they would fall into one of three different categories, okay? So I'm going to start with one over here on the left, where this is electron energy measured in electron volts, and I'll talk about what that unit means here in a little bit. And so we've got something like this, where this is EC plus chi. That's a fancy Greek X. And then down here we have EC. Here we have an energy level called EV. And then down here at the bottom, we have 0. Okay. So this is the energy band structure for what we're going to call an insulator, okay? And this region right here is the valence band. This region right here is the conduction band. And then this region right here in the middle is the band gap. Which typically has a symbol E sub G, okay? So for an insulator, this band gap is very large, and all that means is that it takes a very, very large amount of energy to move an electron from the valence band, which is typically completely full of electrons, up to an empty energy spot in the conduction band, okay? So because it takes a very, very large amount of energy, if we're relying on only a moderate amount of heat and random Brownian motion of electrons, the chance of an electron ever bridging that gap is effectively zero. So that's why insulators behave as insulators. It's just too much energy to overcome to allow conduction to occur, okay? On the opposite side of the spectrum, we have metals. So similar diagram here. Here is EC plus chi, and for what it's worth, chi is the electron affinity. Here's EC, and then let's put 0 down here, and let's put EV here. So what I'm attempting to illustrate here is that the valence band and the conduction band overlap, okay? So for this case, with a metal, it is very easy to, or actually, I say it's very easy to make it conduct. We don't actually have to do anything to make it conduct because there's already a lot of electrons available for conduction in the conduction band. So they don't have to overcome any electrical potential barrier in order to be free for conduction. They're already in those available energy states, right? And then between those two things, we typically have a semiconductor, right? So let's put semiconductors over here on the right. So in a semiconductor, similar graph, let me scooch this up a smidge. It's going to look very similar to what we had for an insulator, except that the size of our band gap is going to be significantly smaller, okay? So here's EV 0, EC, EC plus chi, and this EG is approximately, I'm going to call it 1 electron volt. For some materials, it's a little bit smaller than that. For other materials, it's a little bit bigger. For what it's worth, silicon, which is what we're interested in, has a band gap equal to 1.12 electron volts. So it doesn't take a crazy amount of energy by any stretch of the imagination to cause an electron to leave the valence band and move into the conduction band, but it does take a considerable amount. So let's look at energy band gaps for silicon specifically at different temperatures, okay? So let's start by looking at things at T, sorry, that should be capital T, not time, temperature, is 0 Kelvin. So at absolute 0, our crystal structure, which I'm going to attempt to draw on the left-hand side, and our energy band gap are going to look something like this, okay? So crystalline silicon is highly ordered. So something akin to this. These are my silicon nuclei. And each silicon atom is covalently bonded to its 4 closest neighbors. Now, in a 3D configuration, these would be tetrahedral bonds, but I'm not even going to attempt to draw that. So instead, I'm using a simplified planar representation. Okay. So we've got all of these covalent bonds. So let me just make a note here. So these double lines represent covalent bonds, which means electrons are shared between the 2 atoms. And each of these circles with Si written in the middle of it represents a silicon nucleus. Okay. So at absolute zero, our energy band diagram is going to look something like this, right? So here's EC plus chi, EC, EV, 0. The distance between the energy bands, EG, is 1.12 electron volts as mentioned above. And I'm also going to add another energy level here. This is what's called the Fermi energy level, and it has to do with Boltzmann statistics, which we won't get too deep into the weeds on here because this isn't a class specifically dedicated to semiconductor behavior, but effectively it just represents an energy level where probability that things are going to be filled is 50% below this. I'm probably butchering that, but it's not particularly important here anyway. Okay. So at 0 degrees Kelvin, there is effectively no thermal energy in our system whatsoever. So there is no way in hell that an electron is capable of moving from the valence band into the conduction band. Okay. Now, for temperatures greater than 0 degrees Kelvin, we are going to have something fairly similar in our structure, right? So here's SI, SI, SI. So we've still got most of our covalent bonds in place. But every now and then, one of our covalent bonds will effectively become stretched due to interatomic vibrations. And so we'll see that one of these covalent bonds is going to break. And when that covalent bond effectively breaks, we wind up releasing an electron and a hole. And these are our two charge carriers in a semiconductor, right? So on the energy band side of things, we now have something that looks like this. So 0, EV, EC, EC plus chi, EG, still constant, 1.12 electron volts. Our valence band is effectively filled, but we're going to have a hole here in our valence band, and an electron is going to be able to jump up into our conduction band. It sees thousands upon it will meander along and then wind up occupying the lowest possible energy state until it finds a corresponding hole, and then the electron hole pair is annihilated, right? So for some brief amount of time at extraordinarily low temperatures, we have electron hole pairs and then they're going to recombine, right? As we increase temperature up and up and up, the probability of an electron being able to move from the valence band into the conduction band increases, okay? And when our crystal achieves thermal equilibrium, so at thermal equilibrium, the thermal generation rate of electron hole pairs, which I'm going to call EHPs from here on out, is equal to the recombination rate, the rate at which electron hole pairs are annihilated, and thus the electron E minus and hole H plus concentrations are equal. So I'm going to write that as a mathematical expression. That should look more like an N and not an eta. My apologies. So N, this is our electron concentration, typically measured in electrons per cubic centimeter of a sample. So I'm just going to write that as centimeters to the -3 power, is equal to P, which is our hole concentration, also measured in per cubic centimeters. And this is equal to Ni, which is what's known as the intrinsic carrier concentration, measured in, you guessed it, per cubic centimeters. Okay. So there is a law dealing with these relationships. Okay. So I'll just put it down here, but effectively N times P will be equal to the intrinsic carrier concentration squared. And this is what's commonly referred to as mass action law. And it governs how our carrier concentrations are going to behave when we do things like introduce dopants and all of that kind of good stuff, which we're going to talk about here in a moment. Okay. So the intrinsic carrier concentration and dependent on the temperature and the material again in the form of the band gap. So our expression is going to be B times T to the 3/2 power times the exponential of negative our band gap divided by twice K subscript B T. And I'll talk about some of these things here in a moment. Okay. So this quantity B here in a couple of textbooks, and this annoys me, is literally just called a material dependent parameter. And this material dependent parameter has units of Kelvin to the -3/2 power times centimeters to the -3/2 power. So I want to rant briefly about what that material dependent parameter represents. And it is effectively a combination of the effective density of states in the conduction band, the effective density of states in the valence band, the effective mass of holes, and the effective mass of electrons in a semiconductor material. That being said, this isn't a course on semiconductor physics, so we don't actually care about any of those things. So B is okay, all right? So it is dependent on, the value of that quantity B is dependent on a whole lot of quantum mechanical things that we don't particularly care about in this particular context, okay? T, once again, is simply temperature measured in Kelvin. We've already talked about band gap and all of that kind of good stuff. So let's take this KB thing here. This is Boltzmann's constant, where KB has a value of 1.38065 times 10 to the minus 23 joules per Kelvin, or 8.61733 times 10 to the minus 5 electron volts per Kelvin. And just for those of you that aren't familiar with an electron volt, it is a unit of energy, okay, where 1 electron volt is simply equal to Q, the charge of an electron or proton, which will have the same charge as the whole, multiplied by 1 volt. So that would look like 1.602 and some change times 10 to the minus 19 coulombs times a volt, which is just 1 joule per coulomb, comes out to be 1.602 times 10 to the negative 19 joules. So that's what an electron volt represents. So we're going to see this quantity KBT fairly often. So we're going to give it a special name. KBT is what's known as the thermal voltage. Okay. We might also see a symbol V subscript T for it, where I'm using the lowercase t because I don't want it to be confused with the uppercase T you might use for threshold voltages for MOSFETs and all that kind of jazz. But anyway, and this is going to be effectively something really close to 25.9 millivolts, which we will just round slightly further to 26 millivolts for the sake of simplicity at a temperature of T is equal to 300 K, the generally accepted value for room temperature. Okay. All right. So how are we feeling thus far? Do I need to slow down? Few of you guys are shaking your head yes. All right, I will sit here for a moment until you tell me to go off to the races again. Sorry for being a maniac. Sarah, how are you? Sandra got you grading a ton of stuff for
It's not yet.
okay, but soon.
I have a completely unrelated question for the class.
Sure.
So for MOS, body effect, is body effect only associated with the source that's closest to the body? Because like in integrated circuits, it's a symmetrical device.
Right. So about how to explain. So you're 100%, this is a tangent completely unrelated. Actually, let's talk about it after class so that this isn't wasting 15 minutes. Yes.
The -9.
Oh, sorry, this should be -19. I just missed that. That's it. So handwritten typo on my part. Yeah. Thank you for that catch. I did not just magic up a factor of 10 to the 10. Yeah. All right. Are we good to this point, we've talked about intrinsic semiconductors and all of that kind of good stuff. So at normal operating temperatures, read that as approximately 300K. Most semiconductors conductivity is still quite low. So for example, for silicon at 300K, the electrical conductivity, so that's symbol for that is going to be sigma sub E. Let me write conductivity here. Measured in, feel like it's centimeters per ohm. Did I ever write it down? Electrical conductivity. Resistivity is usually measured in ohms times meters, right? So this would be per ohm per meter. Yeah, it should be the reciprocal. All right. So per ohm per meter. Let me write that capital omega a little less shittily for you guys. Is equal to about 3.013 times 10 to the minus 6 per ohms. Oh, I didn't realize I had it literally right there. Excuse me, per centimeter. Okay. Could call them mo's as well. Yes. Not going to, but I could. It is a commonly used thing. And for comparison, copper at 300K has an electrical conductivity of about 5.952 times 10 to the positive 5 per ohms per centimeter, right? So that's a difference in magnitude of about 10 to the 11. Okay, so huge difference between the conductivity of good conductors like metals at room temperature and semiconductor materials at room temperature. So in order to make our semiconductor materials more conductive, we add stuff to them at incredibly low concentrations. Okay, so we're talking about parts per billion to parts per million at an absolute maximum, but it's able to impact the electrical properties of our semiconductor materials in a very large way. Okay, just to make sure that's an E. So to make a semiconductor material more suitable for electrical conduction, dopants or impurities are introduced. Okay, so let's talk very briefly about acceptor dopants. So acceptor dopants that are commonly used in CMOS processes are elements like boron and gallium. And they typically only have 3 valence electrons, valence separate E minus. Okay, so when they are added to a semiconductor, they create excess holes in the valence band yielding what we're going to call a p-type material. Okay. So I'm going to draw a picture of effectively what's going on for you guys. And this is from the context of an energy band diagram, but I could also do a crystalline structure simplified thing really quickly as well. Okay, so let's think about it like this way. So here's my silicon atom, another silicon atom, yet another silicon atom, silicon, and then let's throw a boron here. Silicon, 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 and silicon, right? So all of my silicon atoms have 4 valence electrons, so they're still going to try to bond to their 4 nearest atoms. But our boron here only has 3 valence electrons. So it's not going to have this double covalent bond to one of these silicon atoms. Instead, it's only going to have a single bond and then a hole that can move off and do whatever the hell it is that it feels like, right? So we've already sorry, I should have a double bond down here as well. So by this very nature, we already have holes available for conduction, even at extremely low temperatures, right? And the number of holes that we are going to have is dependent on the number of boron atoms that we add to our silicon. Now, I've drawn this as effectively a substitution impurity, meaning that one boron atom is replacing a silicon atom, but we could also have interstitial impurities and all of that kind of stuff, meaning that they're not going to fit neatly into the crystalline structure. But again, this is not a class on semiconductor physics, so we don't really care about that here. We're more interested in the fact that for every one of those boron atoms, we get a hole, okay? So what happens in our energy band is, I think, fairly interesting. So that's why I'm going to force you guys to listen to me talk about it for a moment. So once again, we have our basic energy band structure. So here is EC plus chi. Here's EC. Here's EV. Here is, sorry, that shouldn't be E naught, that should just be 0. And down here, very close to the valence band level, those extra acceptor atoms are going to have their own associated energy level, which I'm going to call EA. And the distance between EA and EV is usually on the order of 0.05 electron volts, right? So significantly smaller than the energy band gap we see, or the amount of energy we see between the edge of the conduction band and the edge of the valence band. So effectively, we've got this new available energy state that makes it really easy for electrons in our valence band to move into these energy states and leave behind holes, right? Typically speaking, at least for silicon, at room temperature, practically all of our acceptor atoms should be fully ionized, meaning every single one of them should contribute a hole into our crystal available for conduction, okay? So if the number of acceptor atoms, this is what Na is, so let me write that. measured in acceptor atoms per cubic centimeter is much greater than the intrinsic carrier concentration, then our hole concentration will be approximately equal to Na, and our electron concentration will be approximately equal to Ni squared over Na. So if we have a whole bunch of boron atoms or gallium atoms or anything like that, we should expect to see that our electron concentration is damn near zero, or several orders of magnitude smaller than our hole concentration. Okay. On the flip side of things, donor atoms, like can't even remember what phosphorus, sorry, and arsenic have 5 valence electrons, okay? So when they're added to a semiconductor material, they create excess electrons and yield what we're going to call N-type materials. So I'm not going to bother drawing the crystalline structure shitty diagram here because it's effectively going to be the exact same thing. You would just replace boron with arsenic, and instead of having a hole, you would have a double bond and then an electron over here, right? So very similar picture. I'm not going to bother drawing it. From the energy band side of things, it's also going to look very similar to what we had a moment ago, but just kind of that extra energy level is going to be up close to the conduction band as opposed to down close to the valence band, right? So here is EC plus chi. Here's EC, EV, 0. Now we've got an energy level E sub D here, and it is very easy for electrons to jump from this level up into the conduction band, leaving behind holes in this dead band that don't really do anything, okay? So for this case, if ND, the number of donor atoms, once again measured in atoms per cubic centimeter. Sorry, that double greater than sign looked extra shitty. My apologies for that. Is much greater than Ni. Then our electron concentration is effectively equal to Nd, and our hole concentration is effectively equal to Ni squared over Nd. All right, I've got 10 minutes left. I think I can finish this because this part is pretty damn brief. Okay, so we've talked basically about semiconductors, not necessarily how to dope them, although that was covered in the fabrication processes, ion implantation, all of those kind of good things, thermal diffusion. So we've talked about what's going on here. Now let's just talk very briefly about moving them around, right? So charge carriers in semiconductors move through one of 2 different transport mechanisms, drift and diffusion. we're not going to worry too much about diffusion in this class because we are going to assume that all of that has already happened as part of our fabrication process. And so we're only going to worry about drift, meaning we are intentionally applying some sort of electric field in order to force carriers to move in a direction that we want them to. Okay, so that's applying a voltage, applying a current, or something like that that's causing a net movement of charge carriers, right? So let's just call this very briefly carrier drift. Okay. So when an external electric field is applied to a semiconductor, let's just leave it as semiconductor. Can't think of a better word for medium or anything like that. The field exerts a force on the charge carriers, both electrons and holes, which causes current to flow. And mathematically, we're going to describe this as J, a current density vector, is going to be equal to Q times N, the number of electrons or our electron concentration, times mu sub N, which is the, oh my God, I'm having a total brain fart here. Electron mobility, thank you. Plus P times mu sub P times E, where this is our electric field, okay? So current density, typically measured in amps per meter squared. Q is once again the charge of an electron. We had this as 1.602 times 10 to the negative 19 coulombs earlier. I'm going to leave it as that. We've already talked about N and P. So I'm just going to put mu N and mu P as our carrier mobilities. They're going to be different numbers for electrons than they are for holes. And carrier mobility is typically measured in centimeters squared per volt seconds. And then lastly, we have electric field, which is measured typically in volts per meter. Well, this whole thing right here, so everything that isn't electric field, is our electrical conductivity. Okay. So we can see very easily that we can force the conductivity to increase by introducing dopant atoms, right? So if we put in a whole bunch of donor atoms, we are going to cause the electron contribution to the drift to get very large. If we put in a whole bunch of acceptor atoms, we are going to cause the whole contribution to the drift current to get very, very large, okay? So the last thing that I want to mention here rather briefly is that the resistance R of a semiconductor, or literally anything else, is given by the following relationship that is dependent on conductivity and then the geometry of the resistance, right? So that's going to be the length divided by electrical conductivity over area. Okay. Where, just for the sake of argument, if I had a section of semiconductor material, and I was trying to drive a current through it in this particular direction, this would be the length. And this surface would be the cross-sectional area. Okay. And I'm pointing that out specifically because when we make resistors and stuff like that out of semiconductor materials as part of, say, some piezo-resistive sensor, like an accelerometer, pressure sensor, and things like that, we have to be careful about how we set things up so that we understand in which direction the current's going to flow and all of that kind of jazz. So that's why I'm being nitpicky about explicitly defining the cross-sectional area is going to be orthogonal to the direction of expected current flow. All right, that's enough ranting out of me. So feel like we're going to talk about noise next.